Now we have a bunch of particles which are accelerated, different accelerations, okay, different curvatures. And I'm going to say, well, this is some kind of a warp time. And obviously this diagram is inadequate to represent a warp time. But I'm just going to imagine that I can create some kind of mathematics in which I can formally define that kind of thing. It would not surprise me that these will now change shape in that other diagram. Okay? If one could create a space-time where the time is warped in some sense, warped in a sense that we can call curved, in the sense that it uncurves the world line. Okay? So it's very important to get, what does it mean? Why do I say it's warped? Well, it's clear. Why do I say it's curved? Only in the sense that it uncurves a world line. But it'll only uncurve a specific world line, that which has that curvature. Okay? Now also, if I create this theory, it'll be some kind of abstract mathematical theory, right? In that theory, I'm going to have probably some more complicated quantities that talk about the curvatures of things. But I still, however complicated that the equations will be, I kind of have a naive expectation that somewhere in that complicated theory, I'll have some quantity which describes time axis, and I will have the expectation that it will be somehow equal to, in some limit, the curvature of a specific accelerated particle's world line. Okay? So now, what would happen in a region of space during a particular time, so I'll call it a region of space-time, if time was in fact warped in this sense? And I'm going to say it's in the context, when I say time is warped, it's within the context of space-time, because without having the space axis, I can't really define anything. I don't know what this is talking about. Okay, what will happen, you have a bunch of particles, they're all accelerating every which way, and it enters a region where, let's say, time is warped in this way. So some of those particles will turn out to be inertial, if they have the right kind of acceleration. Or conversely, if we warp the time suddenly, then some particles will start to accelerate that were inertial before. Correct? Now, one of the things that would be interesting is that, let's consider what would happen, let's say we have a bunch of different particles with different accelerations, and not only that, but for every given acceleration, we have particles of every different mass and size and so on. We have big rocks and boulders, we have pebbles, we have particles of dust, whatever, all kinds of different masses. And we give, let's say, we give an acceleration this way, acceleration that way. What will you notice that is unusual? Usually when you find a particle suddenly starting to accelerate, where now we're expecting it because of this warping of the time in this region, we know that acceleration is f over m, generally, right? So acceleration generally is inversely proportional to the mass, correct? So you would expect, somehow naively, that in this case, if you have 10 different particles, right, but they have different masses. So what happens? What should happen to them? Should they accelerate at different rates, or what would you expect? Acceleration is force over mass. Usually when something accelerates, it's due to a force. Here we're saying we're going to warp the time axis, and that's going to cause an acceleration. Does it cause an acceleration the way that a force would cause an acceleration, so that the resulting acceleration somehow is inversely proportional to the mass? What do you think?
I'd guess no, but
why? Not sure. Okay.
Yeah.
Any opinion? It's okay.
I'm just trying to see how time might affect that.
Okay. All right. We'll get into that.
Can you restate the question?
Okay. Sure. We know that an inertial particle has a straight world line. A curved world line means that it's accelerated. We're kind of going to enter a region where the time line, the time axis, time itself, is somehow warped in a sense. So it'll uncurve certain lines and curve others. So what was an inertial particle starts accelerating, and what was an accelerated particle, certain accelerated particles with the same kind of curvature, will suddenly consider themselves inertial. Will that be mass dependent? Because this seems to be like a force. A force causes things to accelerate, or stops them from accelerating, makes them inertial. If they have the right acceleration, put a force, exactly the right amount, it'll stop it from accelerating and it'll be inertial.
so I'd say wouldn't be mass dependent.
Because?
Well, that didn't say anything about mass.
Right.
And if they would all change the same mass.
What I'm doing here is directly changing the curvature of the world line. It has to do with the time somehow. Somehow warping the time, we have this naive intuition, hand-waving thing, speculation that if we could do this, it would change the accelerations, not in a way that's dependent on the mass. It's just makes accelerated particles of certain type inertial and certain inertial, you know. Now, that is a very weird thing, goes against all around intuition because forces generally are mass dependent. Is there any phenomena like that in the universe that doesn't depend on mass? Right. So in other words, if there was a possibility of creating a mathematical model which would do this kind of thing, it could be a model of gravity. Because it has exactly the feature, the very special, unique feature of gravity that only gravity has, that it isn't mass independent. That's called the equivalence principle. And maybe I'll refer to it as the EP just to save time. Okay?
How is electrostatics mass dependent?
Electrostatics.
Yeah.
You have QQ over R squared. That's the force. The acceleration with which it moves in response to that force will be that force divided by m.
And don't you write the force as QE, which is
The force is QE. What's the acceleration? That force divided by mass. Okay. In gravity, generally we did GMM, both m's, the source and the whatever it's being acted on. We usually consider a big source and a particle because we don't want to have to consider the two. We just say there's one big source, it's creating the gravitational field. We ignore the gravitational field of the small guy, and we just say it's interacting by being deflected, that's all. And then we divide it by its own mass. A is F over m. The mass disappears. So it's very clear immediately that a model of time warping will produce gravity. Now, of course, one would have to adjust all the parameters and so on to get the equations. But the equivalence principle maps directly onto this picture. So if one could do something like this, it has directly the potential to be a model of gravity. And in fact, one can do something like this. That's what general relativity does, basically. It constructs something like this. And that's why the Einstein equations turn out to be a model of gravity plus many other things. Okay? So already, this is just the beginning, but we already can see where this is leading. All right? So now, let's look at gravity in the light of the equivalence principle a lot more seriously.